So hopefully you have completed your textbook activity about the types of magma. While in your homework or your little assignment, you learned a little bit about all of the types of magma. We're really going to focus on the three most common today. And we're going to start by discussing basaltic magma. Basaltic magma is often referred to as mafic magma as well. So that word mafic, that really comes from the two very common elements that are in mafic magma or basaltic magma. And those elements are magnesium, which is the Ma part of it, and iron, which is the Fic part of it. If you remember from our previous chapter, the chemical symbol for iron is Fe, and so that's where you get the Fic part for iron. And so this, I'm going to show you just a short little video clip about sort of demonstrating, if I can drag it over here, there we go, demonstrating a basaltic lava flow. So this is in the Big Island of Hawaii, and you can see an active basaltic lava flow. You can see a person very bravely putting a stick in there. You can also see how very close he is to this lava flow. You can see this lava flow is progressing very steadily. Oh, there's some trash. Over some older basaltic lava flows, and but it doesn't particularly seem like people are really worried about their safety in this video, and that's important for today. So, characteristics of basaltic magma is that they are relatively high density, and if you remember, basalt is the primary component of ocean crust. So, and ocean crust also subducts at subduction zones because ocean crust is a higher density plate than continental crust. So it's composed primarily of basaltic rock. And because there is that high concentration of iron and magnesium, it generates a higher density plate that will subduct. You can also see from that video that the lava flow was relatively fluid. There wasn't a lot of explosions associated. It was very sort of casually approached. There was no running, there was no screaming, and that is partly due to the high amount of iron and magnesium in the lava flow, but also when we think back to your homework, it's partly due to the lower amounts of silica in the lava flow. Also, basaltic lava is high in iron and magnesium content and low in general in silica content. We find basalt, again, primarily comprising the ocean floor as well as volcanic islands like we just saw in Hawaii. So this is sort of one end member of the types of magma that you can have. A second one is found in situations that look like this. So here you see a cone-shaped volcano, just like we did when we did the exercise on why volcanoes don't all look the same. This is a composite cone volcano. It is composed of pyroclastic flows, which are those big explosions of gas and heat and ash and sometimes rock and lava from the summit of cone-shaped volcanoes. They're also composed of what's called intermediate magma, or often called andesitic magma. So you'll hear the word intermediate and andesitic used interchangeably. And andesitic lava flows are generally more explosive than some of what you see in a basaltic lava flow. So here you see andesitic lava shooting out of the summit of a volcano in the Philippines. And this is a pyroclastic flow coming up from the surface. This is under high pressure, so the heat and gas is moving up. The lava is erupting, cooling as rock, and then you can also see some pyroclastic flows rushing down the flank of this mountain. So let's learn a little bit about some of the lava that is coming out of the summit of this volcano. And again, that's andesitic lava. It doesn't have as many mafic minerals in it. There are still a higher concentration of iron and magnesium than we see in more silica-rich lava flows, but in general there's less iron and magnesium than we see in basaltic lava flows. You saw from that video that it is generally associated with some explosive volcanic activity. Pyroclastic flows generally occur when magma is under pressure and then it erupts as lava. What you see in this picture here is that composite cone volcano, but you probably also notice this stream flowing down the flanks of that volcano, and you probably notice the color of the stream because it's kind of distinctive. That's because there are volcanic gases that are often associated with these magma chambers. Those volcanic gases create hot springs. There's sulfur that comes out of the water in the groundwater here, and there's bacteria that have figured out how to take some of that sulfur and turn it into food. We talked about this earlier. It's called chemosynthesis. And basically, what you're seeing here in the color of this stream is just a whole bunch of bacterial mats that are using some of the sulfur associated with this volcano to make food. So where do we find andesitic lava? We find it where we mix together the two end members of what we see commonly on the Earth. So if you remember, basalt is the primary component of ocean crust, and granite is the primary component of continental crust. When you melt basalt and you melt granite and you mix them together, you get an intermediate composition that is called andesitic lava, and that's where you find andesitic lava being generated, where you mix together ocean and continental crust at convergent plate boundaries, particularly at subduction zones. Okay, so if you think about where we find these composite volcanoes, they're usually right along ocean to continent convergent boundaries, like Mount St. Helens, for example, in the Cascades volcanoes in Washington and Oregon. If you think about the word andesitic, it looks like Andes, and that's because the Andes Mountains are right along the west coast of South America, where we mix together ocean crust from the oceanic plate that's subducting and the continental crust of South America. They mix together to form composite volcanoes that erupt andesitic lava. So we sort of alluded to where we're going here, but continental crust is primarily composed of granitic magma, or what geologists also refer to as felsic magma. So felsic magma, the word felsic is a little bit more complicated. The sic portion is silica. So silica is silica SiO2, silica and two oxygen atoms, so silicon dioxide. The feldspars, you actually can see some of them in this picture, and you've learned some of these feldspars in lab. Feldspars is a mineral family. The two feldspars that you've learned about is this one here. Hopefully you can identify from its pretty distinctive color. This is an orthoclase mineral. Orthoclase is a feldspar, and then if you look at the white material here, that is, and I wouldn't expect you to be able to identify it from this picture at all, but this is plagioclase. So plagioclase is a second feldspar mineral. You recall both of them have two directions of cleavage. The way you tell the difference is that plagioclase does not have, plagioclase has striations while orthoclase doesn't. So granitic magma does not erupt very often, and it is a good thing. Granitic magma is highly viscous, and viscous means resistant to flow. We're going to talk much more about viscosity in a subsequent lecture, but just think, when you think about the word viscosity, think resistant to flow. Think like really thick material like cookie dough. I like to think about it as cookie dough, kind of schlumping instead of flowing. So granitic magma is very resistant to flow. In fact, most of it cools inside the crust, or it cools intrusively. So this is when entire magma chambers cool within the earth. And as they cool, part of the reason that they're so schlumpy is because they do have a lot of silica in the magma composition. In general, silica tends to make magma stickier. So if you have a lot of silica, the magma is not going to erupt as easily. So because it usually cools inside the earth, it is the primary component of continental crust. When you think about big old mountain chains like the Appalachian Mountains on the east coast of North America, or if you think about like the Sierra Nevadas where like Yosemite National Park is located, that's where you have huge volumes of granitic magma that cooled inside the earth. And when it cools inside the earth, it forms a rock called granite. So which we'll see in lab if we haven't already. And it's really, really bad when granitic magma erupts. It is highly explosive when it does. So this is kind of a dramatization of what would happen if a really large magma chamber of granitic magma erupted. And that is the one that exists beneath Yellowstone National Park, which is considered a supervolcano. We'll learn more about Yellowstone later in the semester, but it is a massive, absolutely mind-blowingly massive volume of granitic magma, and very, very, very irregularly it erupts. So this is supposed to be a dramatization of what would happen if Yellowstone were to erupt. So you can see some of the really extreme examples of a granitic eruption.
Within an hour of a Yellowstone supereruption, pyroclastic flows could race across the countryside and engulf the valley of Jackson Hole and the town of Livingston, some 50 miles away. Within a 60-mile radius, 90% of any remaining people would be killed. A few might be blown to pieces in the initial blast. Most would suffocate in the heat of pyroclastic flows. But this would just be the beginning. Blowing across the states would be the mother of all ash clouds, an aerial mountain of deadly particles and debris. Yellowstone National Park is the site of a recurring supervolcano. An eruption so large that if it happens again, it will destroy nearly everything within 60 miles. But what will happen next as a mountain of ash begins to spread and then fall? The Yellowstone supereruption could throw ash 15 miles into the atmosphere. The fallout could cover half the United States. 3 days after the eruption, the skies would be dark and deadly. From scientists' predictions, naked science has pieced together a picture of the country after 3 days of ashfall. At 6 times heavier than wet snow, wet ash would cause many roofs to collapse, clog up filters of cars, and ground aircraft across much of the western U.S. Any planes in flight would be in danger of crashing.
So that's maybe not the cheeriest video, but I'd like to remind you that's in a super extreme example of a granitic or a felsic eruption, and it's also incredibly unlikely. So we're going to talk a little bit more about how the composition of magmas can change and how they originate in the future very shortly.